sensors and power module product lines. Our second presenter, Marco Comla, joined Nexperia in June 2023, bringing with him 20 years of experience in the semiconductor industry. He currently serves as Nexperia's Senior Product Marketing Manager for E-Mode Power GaN technology. He began his career as an RF power applications engineer before transitioning to various marketing roles, including technical and product marketing for RF power and Psi-Power MOSFETs. Over the past 4 years, he has focused on power GaN products. So after the presentation, we'll have a live Q&A with Emilio and Marco and their colleague, Sebastian Heinz. So you can submit questions at any time during the session by using the chat box tab that you see on the right-hand side of your screen. So thank you all for joining us. And with that, I'll hand it off to Emilio and Marco for the presentation.
Hello, welcome on this webinar from Nexperia. My name is Marco Comola. I'm International Product Marketing Manager in charge of the gallium nitride. And today I want to share with you the E-Mode Power GaN FET from Nexperia. That is sure the GaN FET is the future of the power electronic. I will show you. So let's start with a quick information concerning the agenda. I want to introduce the GaN technology and the benefit came from using the GaN technology. After, I will share information concerning the power GaN market, the application involved mainly, and our proposal. So Nexperia proposal in terms of E-Mode and Cascode, you will see later. And after, I just want to conclude the webinar just showing you supporting material. In particular, I will share with you one evaluation board that we did and a bridge using one device from Nexperia. So again, let's start. Let's introduce the GaN technology and let's start from a question, easy question. So the why the GaN FET? So surely I have to tell you that the initial market success with the GaN was in low power E-Mode, and so first adopter of the GaN nitride were adapter and chargers, and the possibility to shrink dimension to increase the power on this kind of application was surely not that value or benefit using the gallium nitride. Today, the gallium nitride addresses a new emerging application like a power supply unit and consumer and data centers. But the question is why the gallium nitride, and in general, both Cascode and E-Mode, because you will see we have both in our portfolio, can improve surely the system efficiency. And the improvement can be from 1 to 2%. You improve using the gallium nitride also the power density, because you use a smaller device. You can increase also the frequency of your application, so you decrease also the size of the parasitic element, so like a magnetic element in your BOM, and you increase the power density from 1.5 to 4 by. And you can reduce the power losses because the gallium nitride is a new compound, and this kind of new compound you will see later in this presentation have some characteristics, physical characteristics translate electrical characteristics that reduce the power loss to increase the efficiency. And at the end you have also a cheaper BOM because again increase the frequency, you have a smaller magnetic, a smaller transformer and so on. So you can reduce the BOM cost. The gallium nitride furthermore, so let me say can be used in the DC power, new opportunity like the DC power conversion for home appliance, and you can use for new application, and you can use also for new topology. For instance, let me say one total pole PFC, you have to use a WBG switch just to be used on this kind of application. With the silicon MOSFET you cannot do. And on the right side, you can see just a chart just to show the power versus frequency. And you can see there are many compounds today on the market. MOSFET, silicon MOSFET, there is IGBT, there is silicon carbide, and Cascode GaN and E-Mode GaN. Silicon carbide and GaN are a wide band gap, as you said. And these are, of course, there is an overlap between this technology, and I can tell you that the gallium nitride application are for very high frequency. Target of gallium nitride is high frequency, and for the E-Mode is high frequency, medium power. For the Cascode is high frequency, high power. But I will share with you. And okay, let's start with a comparison. quite nice way to just to show the properties of the gallium nitride, doing a comparison versus the silicon carbide. And if you translate the physical characteristic of these compounds in a diagram rather easy diagram rather, as you can see, so you can note that you have a critical field and an Eiger band gap for the gallium nitride. So at the end, it's translating Eiger voltage capability, smaller QGD. So you have a smaller device, so you increase the power density. So other, let me say, characteristic called the saturation velocity and electron mobility that are higher for the gallium nitride versus the silicon carbide and silicon, they are instead translate in low on-state resistance and the possibility, of course, to work at very high frequency. That is surely a benefit of the gallium nitride. So practically, if I have to give you an idea in terms of products, in terms of devices, for a specific on-state resistance value, practically you have a low gate charge versus using the gallium nitride versus the other compound. So you have low driver losses, and you have low QGD, so you have high DB capability. You have low output charges, so no storage charge in third quadrant, and you have low hard switching losses and low circulating current in soft switching, and you have high mobility. And high mobility is translated, of course, in very low turn-off losses, so channel can be closed very quickly. So again, this is translating lower losses and higher efficiency. And let me go on with some information concerning the market and the application and the Nexperia proposal. So if you see the GaN FET application, and we are focusing the webinar on not automotive applications, surely gallium nitride is used today on the power supply. And one of the applications of the power supply unit is surely the telecom and server. So, and you can see, for instance, the 80 plus and titanium plus characteristic programs, and the requirement in terms of efficiency is match very good with the gallium nitride. So using the gallium nitride in this kind of application, you have higher efficiency, you have a smaller size, and increase the frequency, you have a lower BOM cost, as I told you. And for industry is very huge. I just want to focus your idea on the motor driver and solar panel. And the gallium nitride is suitable for motor control and PV panel, photovoltaic panel. And you have, for the motor control, for instance, you increase the frequency, you have a higher bandwidth, so you have a more accurate control. You have lower EMI because, okay, you don't have oscillation using the gallium nitride, lower oscillation. And you have the smaller size because, okay, again, it's increase the power density, and also in terms of application, increase the frequency. You have then the smaller also bulk capacity. You can avoid the bulk capacitance, just replacing electrolytic parts with the ceramic parts, so you have a smaller size as well. And for both, you have higher efficiency. So this is surely something that is an added value using the gallium nitride for the audio. So for the hi-fi, you have surely, and it's something that is already well known from the market, you have better sound quality using the gallium nitride. And you have higher efficiency in your application, so you can translate, you can increase the power with the higher efficiency. And you have a lower noise, so lower THD and lower oscillation and so on, lower EMI. So it's really a new era of Wi-Fi using the gallium nitride. And for consumer, we already told you, so it's excellent for chargers and adapters, since you can decrease the size of your application, you have lower switching losses, you have higher efficiency, and at the end, you can also think to put the charger adapter inside your application because it's very small. And just to give an idea about the landscape, because, okay, I told you we are the only company that have today the Cascode and E-Mode proposal, the Cascode and E-Mode in our portfolio. So, but there is, of course, the positioning from Nexperia. The Cascode is, in terms of electrical conductivity, in terms of stability and temperature, is a very excellent solution. So the Cascode is for high power and high voltage. The E-Mode is instead for low power, high voltage, and for, let me say, all that is concerning the low voltage, low power, medium power, and high power. And you can see a lot of application. Practically, okay, we just, let me tell you this, we divided the devices, low voltage and high voltage, considering high voltage more than 200 volt and low voltage less than 200 volt, and high power more than 1 kilowatt and low power less than 1 kilowatt. This is the 4-quadrant landscape, 4-quadrant way to share and let me say to position our device inside the market. And let me go on. I just want to focus your attention, of course, on E-Mode today. And the E-Mode is a pure normally off GaN, so it's a pure GaN die inside. There is not a device in cascode like the cascoded one that is normally on in cascode with a low voltage power MOSFET that become normally off. In that case, there is a pure GaN die inside. So, and again, I told you, you have a very low gate charge and a very fast rise and full time, so it's ready for high switching frequency. And just a comparison that you can find on the left side and then the bottom side. So if you compare the gallium nitride versus the silicon at the same on-state resistance versus the frequency, device losses versus frequency, of course, the conduction losses, they depend just from the on-state resistance, so they will be the same. In terms of switching losses, of course, the gallium nitride show the benefit, they show a better performance. And so lower switching losses, higher efficiency. And you can drive an E-Mode normally because the VTH is 1.5 typical value. You can drive at 5-6 volt, so you have a minimal gate drive power. You put normally, and we put it like Nexperia, the GaN die in a package that is a low package inductance. It could be, for instance, a DFN 88, that is or DFN 5060, so 5 millimeter by 6 millimeter, or 8 millimeter by 8 millimeter. And in that case, okay, you have an appropriate bonding diagram used, and just to minimize the parasitic effect coming from the tandance resistance coming from the bonding, yeah. And or a package like a chip scale package, and also in that case you have a very low RLC parasitic, and you have also an excellent thermal dissipation, thermal performance. And what else? So for the GaN, for the E-Mode, of course, reverse conduction, there is no body diode, so the reverse conduction is close to 0. So, and you have a very low output capacitance, output charge, and so very low switching energy in the output. So, and extremely low switching losses. So you have excellent dynamic performance using the E-Mode. And let me go on just to give you some idea, really a quick comparison, the 100 volt E-Mode GaN versus the best-in-class silicon MOSFET. In that case, you can see on the left side an EMT, so high electromobility transistor. And you can see that there is no the body diode, so the reverse recovery charge is 0, is close to 0. So you have very low reverse recovery losses, and it means you reduce the ringing and on switch node, and this is linked to AMI, so you reduce the AMI, of course. So you have also low on-state resistance per area and the figure of merit that if you compare, you can see on the right side the diagram versus the silicon. The silicon have 4 or 5 times at the same voltage, at the same 100 volt. So if you reduce the figure of merit, of course, it means, in other words, that at the same on-state resistance, you have 4 or 5 times lower gate charge. And also, I just want to compare our device that is a GaN FET 100 volt in chip scale package, and you can see the size of the package, 3.5 millimeter by 2 millimeter, close to 2 millimeters, and the output capacitance is 460 picofarad. And instead, if you can see the best-in-class silicon MOSFET that is in a package bigger than a chip scale package and our package, of course, is a 5 by 6 millimeters. Is a 900, is the double at 50 volt. So is again is translating this faster switching and the high switching frequency for the gallium nitride product, and reduce switching losses. So again, you increase the efficiency using the gallium nitride. And just to give a quick view of our product portfolio, let's start from the low voltage. We already released the product at 40 volt bidirectional and 100 volt and the 150 volt. We are completing the product portfolio with solution, of course, in chip scale package, in QFN package, and they are just our solution low voltage. You can easily see there is, let me say, from low to medium power. The 40 volt bidirectional, just to spend more words, are they replace two silicon MOSFET back to back for, let me say, over current protection or over voltage protection for low switch, and so you increase the power density using just one device instead of two. The 100 volt and 150 volt, they can replace easily the low voltage MOSFET, just introducing the benefit using the gallium nitride, so higher power density, and then the possibility to work at high frequency and high efficiency. And just to complete for high voltage, we have product 650 volt and 700 volt. 650 volt, you can see in black what we already released, and 700 volt and 650 volt in red one, you can see just a product we are going to release within this year. So we have product in DFN 80 by 8, so 8 millimeter by 8 millimeter, in DFN 5060, 5 millimeter by 6 millimeter, and in DPAC. And again, they will be ready within this year. In terms of supporting material, of course, anytime you do new devices and you need a new technology, a new compound, you have to teach, let me say, the market, to teach the customers to do the right design, and you have to prepare a lot of documentation. You have to share a lot of tips, tricks. So in that case, okay, the data sheet is something that, of course, you have to do at the beginning, is the identity card of your device. In this case, this is the device is 3.2 million 100 volt, so the GaN FET 100 CBE. And you will find easily on our website the data sheet, but you have to prepare more. Of course, SPICE model, of course, thermal model, Cower and Foster, of course, application node and technical node, just to show, for instance, how you can parallel device, how you can probe the device, how you can read the data sheet, so the understanding of the parameter in the data sheet, some recommendation for design, for circuit design, PCB layout, for instance, the driving, and there is a lot, of course, to be there on the website. And furthermore, you have to do more. I mean, so, and one is surely you have to prepare evaluation board or demo board just to show the performance directly in application. That is normally is an easy application, and but they are used just to show again the performance, how to drive, how to use the product in the application. And this is just the E-Mode evaluation board roadmap. So, and you can see what we have already released. So the half bridge, the NX half bridge GaN R2 BSC, and another board with the 7 million we are going to release soon, and the other boards we are working on. So, but I want to focus your attention on the first one. So the board, the NX HB GaN 3R2 BSC. It means practically Nexperia half bridge GaN 3R2, so the 3.2 million device 100 volt, and this about some cooling package. And just to give an idea of the application, first of all, of the devices, you can see on the left side the size of the package, the size of the die, this chip scale package versus €1 is 3.5 millimeters by 2 millimeters, close to 2 millimeters, the size of the device. And this 100 volt E-Mode GaN FET with 3.2 million maximum value for state resistance, 2.4 million is a typical value. And the evaluation board that we did in Nexperia using two devices, of course, using the GaN FET is quite versatile. Evaluation board is an half bridge configuration that can support most common topology, can easily work like a buck converter or boost converter or class D or motor control, just using more than one board. So it's something that you can use to do many experience with the device. And in this particular board, what we evaluate, the key parameter we evaluate are surely the thermal performance. In thermal performance, I mean, first of all, the efficiency. We are working the continuous operation. We saw the continuous operation of the board and some switching waveforms in two different conditions. So let me go on. And I just want to give an idea of the efficiency and thermal performance. And the efficiency was measured with the CDC converter 48 volt, 12 volt. So the board was using like a buck converter. And in that case, you can see on the right side, the switching frequency changed from 250 kilohertz to 500 kilohertz and 700 kilohertz, 750 kilohertz. And you can see the curve there, the efficiency versus the output power. You can easily see the efficiency is quite good. It's more than 95%. And the output power is very close to 350 watt. And this is translated, higher efficiency is translated, of course, in lower temperature. And you can see at high load, at full load, let me say 32 amps. So the temperature of the device, of the GaN device, is 120, close to 120 degrees. And of course, we use it on the application, heat sink and the fan, 12-volt fan. And let me go on. So we with another switching waveform. So again, we use it like a buck converter. So from 48 volt to 12 volt, the switching frequency set for this kind of measurement was 750 kilohertz, and the load current, the current was 20 amps. And the exercise was just to let the board work in NAS switching, to let the device work in NAS switching. And so we just have the screenshot of low side and high side. Low side turn off and turn on, and the same high side turn off and turn on. And you can see how clean is the waveform. There is no oscillation or quite limited, so the board in this condition is working properly. Yeah? And this is the message that I want to share with you. And now just to conclude, okay, the soft switching waveform, so another kind of application. In that case, the switching frequency is 6.78 megahertz. And this is the frequency used normally for wireless charging, for instance, or anyway for ISM application. In that case, we just change the inductor and we put a simple wire loop that is close to 150 nanohenry inductor. And on the right side, you can see the soft switching waveform at 6.78 megahertz. And also in that case, you can see low side and high side, and you can see there are very clean waveform, and the device, the GaN FET 100 CB is working properly also in this kind of working conditions of switching. And that's all by my side. And I just have to tell you thank you for watching the video, for watching this webinar. And for more information, please visit nexperia.com, GaN FETs. Thank you very much.
Hi, everyone. Thank you very much for joining this webinar. In this part of the presentation, we will be talking about the passive component choices on the NXHB GaN 3R2 BSC, specifically about the capacitor and inductor. My name is Emilio Guzman, and I'm Product Definition Engineer supporting our semiconductor partners in the US West Coast, like Nexperia. Let's get right into it. So the agenda for today covers the following. We will be looking at the components on this design in particular. After that, we will be looking at the aluminum hybrid polymer capacitors. And then what is a capacitor? Then the technology comparison along with characteristics and lifetime comparison, and the benefits for GaN technology. Then the high current flat wire inductor, and what is an inductor? The losses, the winding AC losses, specifically the skin effect and proximity effect, the wire technology comparison, and the benefit of this flat wire inductor for gallium nitride. So for this Nexperia design, we included a total of 17 different unique part numbers from Worth Electronics. In this list of parts, we included an aluminum hybrid polymer capacitor, ceramic capacitors, a high current flat wire inductor, monocolor LEDs, SMA connector, MMCX connector, high current SMD redkip connectors, pluggable terminal block, plastic spacer, shunt connector, and a pin header connector. From which in this presentation we will be focusing in the aluminum hybrid polymer capacitor and the high current flat wire inductor. So starting the discussion about the input-output capacitors chosen for this design, these are our latest aluminum hybrid polymer capacitors, which combine the two main technologies of aluminum electrolytic and aluminum polymer capacitors. These are available in surface mount or through hole. So before jumping into too much of a detail of the capacitor technologies, we first need to understand what a capacitor is. And so a capacitor is an electronic component that stores and releases electrical energy. It's made up of two conductive plates separated by an insulating material called a dielectric. And so if we see in this slide, the basic parts of a capacitor are really just the electrodes, the dielectric material, and the distance between the electrodes. A capacitor is normally used for filtering or energy storage or timing circuits. And we can easily calculate the capacitance by multiplying their permittivity by the area divided by the distance between the plates. And here's something very important to mention is the ESR. So ESR is a key factor and will be mentioned again later on, but it is a small amount of resistance that exists in series with the capacitor's plates and the dielectric. It combines all the resistive losses within the capacitor, including the resistance of the leads, the plates, and the dielectric material. It causes energy losses, and so it reduces performance, it creates heat, it can lead to poor filtering and unwanted voltage spikes. Usually low ESR helps smooth out ripple in a better way. And so in general, the lower the better. And so this will be mentioned again later on. So in this slide, we see the technology comparison between the three available technologies at Worth Electronics. From left to right, we see the aluminum electrolytic with the anode and the cathode separated by a dielectric oxide layer and a paper soaked in liquid electrolyte. Then the polymer with a very similar construction, but only with a separator soaked in conductive polymer instead of the liquid electrolyte. And then lastly, for the aluminum hybrid polymer, the separated paper is soaked in both the liquid electrolyte and the conductive polymer. So this is hence the name of the technology of aluminum hybrid polymer. It's exactly the combination between the two. Now jumping to the characteristics comparison between the three technologies, we can start to see some more differentiation between the three technologies. For the aluminum electrolytic, we start to see the highest voltage ratings up to 450 volts. We see the biggest sizes and other connection types like the screw and snap-in. The properties improve at higher temperatures, and the dielectric self-healing is also an important topic. Although some disadvantages can be that the electrolyte drying can be a problem for long load times. For the aluminum polymer, in contrast, it has very low ESR, it has very high ripple current capability, has a very long lifetime, and it's very stable at low temperatures. Although for the disadvantages, it is limited in voltage and size, it has a somewhat high leakage current, and it could be susceptible to vibration. And now switching to the hybrid polymer, here we see the best of both worlds in the combination. And so we see a low ESR, maybe not as low as the polymer, or sometimes even lower than the polymer. It has high ripple current, it has low leakage current, and it has the best performance of the three over the temperature range. Also, the lifetime is better than the electrolytic, but it has some limited voltage and size, and it has a more complicated production, thus incurring a bit higher cost. So now for the lifetime comparison, we see how the three technologies stack up in the endurance. In the graph on the left, we can see the lifetime in the y-axis in logarithmic scale and the ambient operating temperature in the x-axis. Now, the electrolytic capacitor starts at the bottom with the lowest lifetime, followed by the polymer, and at the top, the hybrid. This is on a range of about 105 to 70, what I'm mentioning. Now, one significant difference can be seen at 65 degrees, where the hybrid and the polymer actually pass the 15 years lifetime, while the electrolytic stays behind at only 3.65 years. Now, this 15 years is mentioned because there are many lifetime factors that are taken into account after that. So it is usually guaranteed up to the 15 years, but after that, there can be many factors that come into the lifetime of the capacitor. And so now for the actual benefits for this design for Nexperia, some of the technical requirements that needed to meet these capacitors were 68 microfarads, a switching frequency range of 250 to 750 kilohertz, and even higher switching frequencies, up to 60 volts input-output, 125 degrees max temperature, and 1.8 amps ripple current. And so if we switch over to the graph in the right, we can see a comparison between the three parts. The three of them are 68 microfarads and the same diameter. And so if we look at the ESR of the three, it is actually the green one, which is a hybrid, which has the lowest ESR in that switching frequency. Then above that is the polymer. The hybrid and the polymer would have been good choices for this design, but the polymer did not meet the minimum voltage. The electrolytic did meet it, but the ESR in that frequency range was too high. And so as Nexperia was looking for the highest efficiency design, it was actually the hybrid capacitor that was the best choice because it met the capacitance requirement, the ESR requirement, the ripple current requirement, and the size. Now switching over to the inductor topic, we will see what the current choice for the high current flat wire inductor was and the comparison between the different wire types. In this case, the WE-HCF comes in lit wire, round wire, and flat wire. And again, before switching to the comparison of the technologies, we also need to understand what an inductor is. And so the inductor plays a crucial role in energy conversion because it works as both energy storage device and a filter. Essentially, any wire is an inductor, but nowadays inductors have these four main parts. It is the wire, the core, the shielding, and the air gap. These four variables combine to provide the inductor with its particular specifications, and often it's trade-offs. Too much of one variable can decrease the other. And so in the formula in the rectangle, we can see how to calculate inductance if all the values are available. So as anything in this universe, inductors also have losses. In this case, the total losses are a combination of both DC and AC losses. DC losses being purely the DC resistance of the copper wire. The bigger the wire gauge, the smaller the DC resistance, or also named DCR. For AC losses, there is a skin effect, proximity effect, hysteresis losses, and eddy current losses. For today's presentation, we are only focusing on the winding AC losses, which are the skin effect and proximity effect. Hysteresis losses and eddy currents are more related to the core losses, so we won't be explaining that today. As for the winding AC losses, the skin effect and proximity effect are also a key factor to take into account when choosing the type of wire for the inductor. For the skin effect, When frequency increases, AC tends to flow near the outer surface of the conductor, rather than uniformly throughout its cross-section. And as the effective area for current flow decreases, resistance increases, thus increasing the losses. Here, a flat wire improves on this, with its geometry helping distribute current more evenly and reduce losses at higher frequencies. For the proximity effect, it refers to the tendency of the current distribution in one conductor to be affected by the magnetic fields generated by nearby conductors. This causes the current in one conductor to push on the current of another conductor, also increases resistance and impacting the efficiency. Here, the flat wire also helps on this issue by providing a larger surface area, allowing the current to spread more evenly. Also, the packing density allows them and minimizes the impact of magnetic fields in other conductors close by. Now, as a comparison between the three wire technologies, we can see the round wire, the flat wire, and the lathe wire. For the round wire, the filling factor is about 30 to 40%. It is cost effective. The losses have a middle ground, and it's simple to manufacture as the round wire is more readily available. Although it has higher AC losses, being the skin effect and proximity effect, as we just saw before. For the flat wire, it has the highest filling factor of up to 60%. It has the lower RDC. It is very efficient for heat dissipation with higher rated currents. And it has reduced the skin effect in comparison with the round wire specifically. Now, it's because of the flat wire, it's more complex to manufacture, and thus it increases the cost. And it also has higher AC losses in comparison to the lathe wire. Now, for the lathe wire, it is more applicable for higher frequencies in the megahertz range, and it has a minimized skin effect and proximity effect due to its packing method, although it has the worst filling factor between the three, from 5 to 15%. And if we took these three wire technologies and picked the same part across the three, we could see the following comparison. These three parts are 33 microhenries and the same core size, but we can see an interesting difference where the round wire has a middle ground DCR. It has a 20 amps rated current, which is already higher than the lathe wire, and it has a higher saturation current, a bit higher than the flat wire. Although here the flat wire has the least amount of DCR and the highest rated current. This would be optimized for when you know exactly when or how much rated current you're going to have without crossing the saturation current. And lastly, in comparison, for the lathe wire, it would have the highest DCR with the lowest rated current and a bit higher saturation current than the round wire. And so in this case, the lathe wire would be more applicable for higher switching frequencies. And you can see this comparison in Red Expert if you click on the link in this presentation. And finally, looking at the benefits of this flat wire high current inductor for Nexperia's gallium nitride design, we can actually see that for this 6.8 microhenry inductor, there is a B variant. This B variant actually has a high permeability core. This high permeability core helps on increasing the inductance and actually decreasing the number of turns while maintaining the same total inductance of the part. So decreasing this number of turns actually helps us increase the wire gauge and increase the rated current and decrease the DCR. And so we can see that this part has a DCR of 0.88 milliohms. In comparison, there is actually no lathe wire part for this inductance, as in this core, the lathe wire wouldn't be able to fit into this package, and it wouldn't actually be able to reach the rated current. And so as this design is not very high frequency, lathe wire is also not very important, as it only working from 250 to 750 kilohertz. And also the round wire would be higher DCR than the flat wire and bigger size as well. So here it's the flat wire that is the best solution for this design in particular. You can also see the comparison between the three parts in the Red Expert link in this slide. And thank you very much. That is all for the explanation of the passive components in Nexperia's design. We will be open for some questions after this, and thank you very much for your time.
Thanks, Emilio and Marco, for that great presentation. We already have several interesting questions from our audience, but I do want to let our audience know that there's still time to submit your questions. So please do on the chat box on the right side of your screen. So let's see if we have our Q&A panel here. Emilio, Marco, and Sebastian, are you ready to answer some questions?
Yes, we are.
Excellent. Okay. First question, what are the key differences between the three